Hello and welcome to this second film about covalent bonding. It's called Covalent Electron Dots 1 and it comes just before Covalent Electron Dots 2 and just after the covalent bonding intro. And this one deals with a method that we're going to use, or that you could use, that always works for drawing electron dot diagrams correctly for covalent molecules. So by the end of this film you should know those rules and practice using them, using a few examples at the end of the film. Okay, so here are the rules. I'm going to go through these quite quickly because you can always pause and rewind. So step one is to count the electrons that you've got. This will make more sense at the end when we go through the examples with each slide. Count the electrons so that you know how many pairs you have to use, not forgetting the charge on the substance if there is a charge. Step 2 is to join all the atoms to the central atom using single bonds. Step 3 is to fill the outer shells of all the atoms you have. And step 4 is to count up the electron pairs that you've used so far and insert any double or triple bonds if necessary. So if you've used too many pairs, this is a way of cutting down on the amount of electron pairs you've got. So here are the examples that we're going to do. We've got a chlorine molecule. So that's quite a nice simple electron dot diagram using just one covalent bond. We've got another diatomic molecule here made of 2 atoms. This has got a different type of covalent bond in it, nitrogen, SiCl4, so silicon tetrachloride, and SO2 or sulfur dioxide. Okay, and then we've got NO3 minus, which we call the nitrate ion. So this is something with a charge, and that's something we haven't come across in the other ones. Okay, so here we go. We're going to go back and use the rules for these 5 examples. Step 1 is count the electrons. Well, we need to know what group our atoms are in. Chlorine is in group 7, so it's got 7 electrons. But we've got Cl2, so it's 2 times 7 electrons, so 14. And that's 7 pairs. Okay? So we know we've got 7 pairs to play with. Now we need to join all the atoms to the central atom using single bonds. Well, there isn't really a central atom in the chlorine molecule because it's just 2 chlorine atoms. So we go like so. Okay, we've got to then fill the outer shells of all atoms. Well, chlorine atoms can hold 8 in their outer shell, so we'll fill their outer shells by giving them 3 more pairs each. Remember, we can draw a pair of electrons as a line. Here's a pair, here's a pair, here's a pair, here's a pair, and so on. So each chlorine atom now has 4 pairs of electrons in its outer shell. Okay, now we go on to the next slide and we count up the electron pairs that we've used. We've used 1, 2, 3, 4, 5, 6, 7, and if you remember we had 7 to play with, so that one's done. Easy. Okay, N2 is the next example, so back to step 1. We need to count the electrons that we've got. So remember here, we need to know what group our atom is in. So nitrogen is in group 5, but we had N2, so a nitrogen molecule made of 2 nitrogen atoms. So we've got 2 times 5, which is 10 electrons. Okay, might just leave this up this time as we do the example. So that's 5 pairs. Step 2 is to join all the atoms again. There isn't a central atom. Okay, so I'm going to join them together using single bonds. Then I'm going to fill the outer shells of all the atoms. Nitrogen atoms can hold 4 pairs, 8 electrons in their outer shell. So there's 4 pairs around that one and 4 pairs around that one. 1, 2, 3, 4. 1, 2, 3, 4. And finally, count up the electron pairs that you've used and insert double or triple bonds if necessary. Well, I had 5 pairs to play with, but I've used 7. So let's put a double bond in. I can take an electron pair off each of those nitrogen atoms because they've both got a full shell by having that extra bond there now. They've both got 4 pairs. I've still used 6, so I need to put in another bond and get rid of another pair on each one. And I've now used 5 pairs. So now this looks like triple bond and unused pair of electrons on each nitrogen atom. Next example, SiCl4. This time we have got a central atom. But anyway, first of all, let's start off by looking at what group? They're all in. So silicon is in group 4. Chlorine, that's in group 7. But we had 4 Cls, so 7 times 4. And that altogether makes 32 electrons, which is 16 pairs. Okay, moving on. We need to join all the atoms to the central atom using single bonds. Central atom is usually the one you see first. So we had the formula SiCl4. The first one's going to be the central atom. So there we go. I've joined them all to the central atom. Well, I haven't yet, but I am joining them all to the central atom using single bonds. Next step, fill the outer shells of all the atoms. 1, 2, 3 gives that chlorine 4. 1, 2, 3. 1, 2, 3. 1, 2, 3. And silicon's already got its 4 pairs, so it's got a full outer shell. Count up the electron pairs we've used and insert double or triple bonds if necessary. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16. So we're done. Okay, what have we got left to do? SO2 and NO3 minus. So here we go with exactly the same rules. So we're starting here with SO2. We've got sulfur in group 6. Remember, we need to know how many outer shell electrons there are. Oxygen also in group 6. But there's 2 of them. So altogether we've got 18 electrons, and that's going to give us 9 pairs to play with. Okay, join all the atoms to the central atom using single bonds. So there's the central atom because it's the first in the list. SO, O. Using single bonds, we're done. Next step is to fill the outer shells of all atoms. Sulfur holds 8 electrons in its outer shell, so it needs another 2 pairs. Same thing for oxygen, except they need another 3 pairs. Okay, so they've all got full shells now because they've all got 8 electrons around them. Count up the electron pairs used and insert double triple bonds if necessary. We've got 9 pairs to play with, but we've used 8 and those 2 makes 10. So I've got to get rid of some electrons, and I do that by putting a double bond in. This oxygen's got 4 pairs now, and so has that sulfur. Get rid of those pairs. I've used 4 and 4 and 1. That makes 9. So just to tidy it up quickly, double bond to one oxygen, single bond to the other, lone pair on sulfur, 2 lone pairs on that oxygen, and 3 on that one. So they're pairs that haven't been used to make bonds. And the final example was NO3 minus, the nitrate ion. So here we go. This one's got a charge, which we haven't dealt with yet. So NO3, it's got a minus charge. Nitrogen is in group 5, oxygen in group 6, but we've got 3 oxygens, and we've got a negative charge, so there's another 1 electron. Add them all up, and you get 24, so that's 12 pairs. Join all the atoms to the central atom. Central one is the first named, so N. Join the oxygens to it using single bonds. Okay, I've used a particular geometry there, but that's not important for waste at all. Fill the outer shells of all the atoms. Nitrogen holds 8 in its outer shell, so it needs 1 more pair. Each of the oxygens needs 3 more pairs, so they've all got 1 each at the moment. Remember, I'm doing this as lines, not as dots, because it's quicker. Count up the electron pairs that you've used and insert double or triple bonds if necessary. I had 12 to play with. I've used 4, 8, 12, 13, so I've got to get rid of 1. And that means getting rid of a pair of electrons from the 2 atoms that I've put a double bond in between. Okay? I'm also going to put a square bracket around this because remember we always do that for ions and it's got a negative charge. Okay, so that's electron dot diagrams for some elements and some compounds, and also some compound ions. So this was an ion, but nonetheless it had covalent bonds in it. How could you tell? Because this ion is made of non-metals joined together. This ion had a negative charge. We added an electron for a negative charge. If you had a positive charge, you'd need to take electrons away. But that's about it here. The next film, Covalent Electron Dots 2, talks about some slightly more complicated examples where we use compound ions to make actual ionic compounds.